Hello again. Okay. Hello again. We have Vlad with us. He's our neighbor. Like so. Yeah. So it's near. Yeah. You will hear stuff about transactions, concurrency and control. So I bet you're going to enjoy it. So yeah, we accidentally opened up lunch, and we could not stop you from eating, which is okay. So you should eat, but yeah, like the talks will continue at the regular schedule, and the lunch will be served and will be open like until basically 15 to 2. So you will have plenty of time. And I have to remind you again, because we are a full tech conference, we are using chatbots to interact with the speakers. This as well is important for a live stream audience. So you as a live stream audience have a way to interact with the speakers. Just fire up the chatbot. You can find him on Messenger and Telegram. It's called Orange Tessie bot. Find him, friend him, and yeah, you will figure it out from there. He's very friendly. So ask questions, and more importantly, okay, they moved it. So there was a rating screen. So yeah, start rating. We have some rates coming in, but speakers really, we have some threshold. Yeah, so they're on the upper right corner of your, there will be speakers, and we have like, they will really appreciate your feedback. So please do rate the talks. And during the talk, when you figure it out, oh, I should get more information, fire up the bot, like just ask a question. It will be here. I will summarize the question so you get the best value, and for Vlad to be able to answer most of your questions. So that's it. I'm giving the stage to Vlad. Yeah.
Right. Thanks for coming to my talk. Today we're going to talk about transactions and concurrency control patterns. Oh, my name is Vlad Mihalcea. I work as a Hibernate developer and developer advocate. My blog, vladmihalcea.com, you can find there hundreds of articles about JPA, Hibernate, relational databases, new SQL, NoSQL as well. That's my Twitter handle if you're using Twitter, and my GitHub account. This talk is based on the transactions chapter in my book, High Performance Java Persistence. And as you will see today, there are many things to talk about on this topic, especially talking about concurrency is always difficult, but when you put into perspective persistence as well, is even more complicated. Now, the reason why I want to give this talk is inspired by this quote from the Google Spanner research paper. Actually, Google realized that they actually, even before Hadoop, they have their big table implementation, and they realized that it's very difficult to work like that. Actually, they needed a database to be consistent, because working without transaction is actually very difficult, and actually they prefer to have a transactional database, and a developer overuse it and have performance problems related to transaction than to deal with issues when you don't have transaction, which is actually the opposite of NoSQL database. So eventually they come out, they invested a lot of money, and they come out with a database, Google Spanner, which is globally distributed and also transactional. Actually, it's quite remarkable. So the bottom line here is, if it's difficult for Google developers to work without transaction, I think it's very much universal. It's difficult for everyone else. Now, when it comes to a relational database, you have to think about that everything you do happens in the scope of a transaction. It's impossible to get out of transaction. You are going to use them even if you don't declare them. If you don't declare them, it's just a scope that is going to include only one statement. That's what we call autocommit, and we usually don't want to use that. Usually we want to set the boundaries where the transaction starts and where the transaction ends, either through a commit or a rollback. Now, initially, when database systems were developed, there were only 3 properties that characterized a relational database. So even before ACID, we had consistency, atomicity, and durability. And we will see exactly what all those means. Atomicity is actually the simplest one. When you declare the boundaries for the start and the end, you enroll multiple statements which either all succeed or then all of them will fail, and the outcome is going to be reverted to the previous state. So that's what atomicity means. Now, in order to have atomicity, we need to have the ability to roll back. Without having rollback, it's impossible to have atomicity. And in order to have rollback, we have to prevent a phenomenon which is called dirty writes, which happens something like that. So assume you have two users, Alice and Bob. We are going to use them for all the diagrams in this presentation. And we have only one, we have this record in the database called post. And first, both Alice and Bob start their transactions. Then we have Alice, which updates the title to ACID. And then we have Bob, which also does the same, but overrides Alice's record. Now, the problem, if you allow a database to do that, the problem comes when Alice tries to roll back. And now it's not clear what should happen. If we revert to the previous state, to transactions, we are going to override Bob's change, which is bad. If we don't do that, and Bob is going to revert in the end, then he will revert to the state of ACID, which actually didn't exist because both Alice has reverted as well. That's why all databases prevent that. At even the lowest isolation level, they have to provide at least this protection against this phenomena. Now, when it comes to consistency, this is a very misleading term because it's used in many contexts. For relational database, consistency means constraints. Moving the database from one consistent state to the other means that all constraints must be validated when you commit. And when you think about constraints, you have to think about types, varchar, integer. You cannot save a varchar in an integer. Length constraints, not null constraints, unique constraints, foreign key. So basically that's what consistency means in the context of relational database. Now you might have heard of this theorem, it's quite popular, the CAP theorem. Now consistency in that theorem is something different, which is called linearizability. And linearizability means that if you have a master-slave replication, for instance, and you have a record which is replicating from master to the slave, and then when you do an update to the master, if you have another client, which the time flows from left to right, if they read right after the update, they will still see the old data. So linearizability is a recency property, but it's completely different than what we have in a relational database. So you have to keep that in mind. Now, durability is a third one, and it allows us to make sure that once a transaction has committed, all the changes are going to be persisted even if we unplug the cable of the database. To understand durability, you have to understand how a relational database works. Actually, that's not just a relational database. Actually, most databases, even NoSQL, work like that. You have the pages for indexing and the tables, you have them split in pages in the operating systems, and they are on disk. However, loading from disk is very, very slow. Even from a solid-state drive, it's like 10,000 slower than reading from RAM. So you want to buffer as much as possible in the RAM. Actually, for instance, I will give you an example. Stack Overflow is the site number 50, and it actually works with just 2 servers. There are only 2 SQL Server nodes that serve all the traffic in the world, and they have billions of queries every month. And it works with only 1 server. How is it possible? And the answer is very easy. They just store everything in RAM, so everything is extremely fast. Every query, every transaction runs actually in less than 20 milliseconds if you work exclusively in RAM. So that's what relational databases do. When you load something, you always load it in memory from disk. And when you modify it, you modify the copy in memory. But during commit, you cannot flush at every commit because it's going to be extremely slow. It's going to incur a lot of random writes, which are going to make your transaction, going to affect your transaction throughput. So actually the database cheats a little bit because when you commit, you don't flush all the changes in memory to the disk. But if you unplug the cable, you are going to lose the updates. So the database does something different. They append all the changes during commit to the redo log. And then they flush that one on every commit. And that's okay because sequential writes to an append-only log are fast. Doing random writes is going to be slow. So, and actually synchronizing the buffer from in-memory to the disk happens from every minute, every 5 minutes, depending on one database to another. So that's exactly what durability is all about. Now, that was before. Now, we also need to address concurrency. So we could have made this acronym ACDC, but it was already taken. So when SQL92 emerged, they actually introduced for concurrency control another property, which is called isolation. Initially, there was no isolation because all databases were supposed to work in the serializable in a serializable fashion. Now, what does it mean to work? What does serializability means? It does not mean that every statement and every transaction is executed one after the other. That's serial execution. It means that we can interleave read and writes in such a way that we get a transaction log that's equivalent to one serial execution, but actually there could be multiple combinations of interleaving, multiple serial execution possible. So it has to be equivalent to only one. Now, a serial execution would have to be something like that. Every user would have to get an explicit and exclusive access to the database. So Alice comes, she reads and writes, then Bob comes and they do the same. Now, if you don't do that, because doing exclusive access would mean that you have maximum one user connected to the database, and that will not probably scale very well. If you don't do that and you don't offer some concurrency control, you'll have conflicts. Like for instance here, Alice is going to read one record, and in between Bob comes, reads and modifies it, and when Alice comes back and modifies the record, she will not know that the record has been modified. So she will overwrite the change of Bob without knowing it. So that's a conflict, and we don't want to have that. We want to prevent it. And there are two ways to prevent conflicts in any systems which provides concurrency. You can either avoid it. VDB does that. It works like Node.js. When you don't have threads, when you have only a single thread, you don't have concurrency, you don't have any concurrency problems. In VDB, it works because everything is in memory. So working with data exclusively in memory can be actually very fast. So actually, they realize that adding concurrency control is going to work slower than executing everything in a single loop. However, relational databases don't work like that. They allow you to work with multiple database connections, as you know. And for that, they have to control it somehow, and that's done through concurrency control mechanisms and isolation levels. Initially, there was only the first implementation for serializability was two-phase locking, which actually not only that it provides serializability, it provides strict serializability, which means it's you get both serializability and linearizability, the property we saw earlier. Actually, every transaction is executed and is nicely ordered in time, just like the statement are also executed. And the second options you have is multi-version concurrency control, which is actually very popular, and most database systems that you use today actually use this one instead of two-phase locking. And we will explain how those work. Now, both two-phase locking and MVCC have to use locks. It's just that MVCC uses less locks than two-phase locking, but actually all databases have to use. And there are two types of locks. Actually, that's not just for databases. You also have it in Java too. You can have a read or a shared lock and exclusive lock. The shared locks, once you acquire it, allows you to acquire another shared lock, but you cannot acquire an exclusive lock. And the exclusive lock, once you acquire it, you prevent both shared and exclusive lock from being acquired until you release them. Two-phase locking works very simple. Once you read, you take a shared lock. Once you modify, you take an exclusive lock. All the locks are acquired during the transaction and released after you commit or you roll back. The way it is conceived to work like that, it provides you, it's actually demonstrated mathematically that it provides you strict serializability. However, the cost of locking is very high. And you might know this Amdahl's law. Have you ever heard of Amdahl's law? It's a property which tells you that you can parallelize an execution by the percentage of your algorithm which allows for parallelization. If you have a serial execution like using synchronized block and stuff like that, then that will limit how much you can parallelize your algorithm. But however, there's this mathematician, Neil Gunther, who was working in the 80s, and he realized that if you take a look on Amdahl's law, you realize that it virtually scales infinitely. So you can just add more threads. How that translates? You have a JVM, and you just spawn 10,000, 100,000 threads, and you see that it just scales goes to infinity, which actually is not correct, because you can simply emulate this by just adding more threads to your application. Actually, is going to work worse. And actually, the curve goes something like that, because the cost of concurrency between multiple caches that you have in processors, between caches that you have in databases, is going to affect you. And the context switches and the concurrency cost actually is going to work against you. So using less locks actually is actually better for a relational database, because in a relational database things are extremely concurrent. Now, two-phase locking was invented in the 80s, when, for instance, this was taken from Jim Gray's paper, when they say that back then, in 1981, the largest airline system used 10,000 terminals, and you only had like 100 active transactions at any given instance. However, even on my laptop, I can take MySQL or Postgres and deliver more transactions than that with a simple database, with 16 gigabytes of RAM nowadays. So challenges have changed. So nowadays, you cannot just use two-phase locking, because it's not going to scale very well. So that's what most database systems that you use MVCC. And we will see exactly how it works. The principle of MVCC is that readers will not block writers, and writers will not block readers. Only writers block writers, because you want to prevent the dirty write conflict, because you want to have atomicity. Now, if you take Postgres, what's interesting about it is that you can actually visualize how MVCC works. Every table, besides all the columns that you declare, also have some additional columns. Some of them are Xmin and Xmax, which are used for visibility, to declare if you are allowed to see a row or not. So when you are going to, for instance, you can actually get your transaction ID, and when Alice is going to insert one record, that record is going to be inserted, but it's going to only be visible for Alice alone. Bob is not going to see it until Alice commits it. And when you add such a record, you are going to set the Xmin with your transaction ID, which means that transaction IDs which are greater than Xmin are going to be allowed to see it, because it happened before your transaction has started. So only after Alice commits, the other threads are going to see it. So that's how inserts work. Deletes, assuming you have this record which has the Xmin set, and now we have Bob who tries to delete it. So actually, when you delete it, you're not going to physically remove the row. You just set, deletes are very fast. You just set the Xmax, which tells what's the maximum transaction number that is allowed to see that record. Every transaction that comes afterwards is not going to see it. So only when you commit, if Alice in the same time after Bob's commit, they are going to see the record, but they can even see the Xmax going to be set there. After Bob's commit, the record is going to be still there, but it's not going to be visible. So actually MVCC plays with visibility. The rows are still there. They are going to be recollected by a process which is similar to the garbage collector process which you have in Java. The update is exactly a delete and an insert. That's how it happens in Postgres. In other databases, they use rollback segments. But here, when you do the update, you are going to actually delete the old state, and you are going to recreate a new one. What's nice about it is because you have two versions of the same record in the same time. Until you commit, other transactions are allowed to see the old state. That's why you don't have blocking, because you have multiple versions. So you don't need to block, because other transaction, until you commit, can still see the record how it was before you modified it. Now, when it comes to MVC, there are two types of isolation levels you can get, which are based where you put your reference. You can put the reference to the time the transaction has started or the time of the query. And of course, you have to be aware of long-running transactions, because that don't work really well, because they prevent the garbage collector process from reclaiming all state. When in SQL 92, when you read the paper, you'll see that there are only 3 phenomena. However, that's not very updated, because in reality you can have more. In the paper you know that you have dirty read, non-repeatable read, phantom read, but in reality you have more, like dirty write, which we just saw, read skew, write skew, and lost update that can affect your application. You have to be aware of it, because some of them can happen, and usually happen, in the default isolation level that you use for your relational database. Okay, so the dirty read how that happens. You have a row, you have a user who modifies it, and Bob, the other user, reads an uncommitted modification. The problem comes when Alice rollbacks, because Bob's might take a decision on a row that actually does not exist anymore. If you take a look on the transaction log and try to understand what happens, you will not know, because that row was rolled back, so it was reverted. Non-repeatable read happens, for instance, when you have one user who reads a value, and then in between you have another transaction who modifies and commits it, and when you read it again, you are going to see the modified value, but in between you might have executed something, and you have to roll it back. So the problem here is, even if you don't read it again, you might take some decision on some old values that are not relevant anymore. Phantom read is actually the same, but it applies to range of records. Instead of one record, you apply to a range of values. So if you select all the post comments for a given post, and in between you have a different user who appends a new record, and you do another select, you're going to see it. That's how phantom read. That's where the standard ends. In reality, you have more than that. For instance, read skew is only, all the other ones are relevant more for MVCC databases. They're not put in the standard because the standard actually assume that you are going to use two-phase locking, which is not relevant anymore. So the read skew, for read skew, you have to have two rows which have to be synchronized. Like a post must be written together with a post detail which marks who made the modification. So now you have one user who tries to, they want to read both, but between reading the read and the reading the post and the post details, you have different transaction who comes in, modifies both records. So by the time you read the second record, you actually read the first one from the previous state with the second record from the other state. So you assume that the row with the title transaction was written by Bob, but this combination never existed. Write skew is different. You have both users reading both records. Now, you want to, Bob's realizes that the post details is the same. So even if they modify the updated by column to Bob, that's not going to be updated if you use JPA or Hibernate. So they are only going to update the post. And Alice realized that she wants to set the post with the same title, but then that row is not going to be modified, only the post details is going to be modified. So if you allow this, you're going to allow an interleave between two different records, so they are not going to keep this constraint between these two records that we have set before. The last one is the lost update, which we also saw previously. You read one record, in between, afterwards you have a different transaction who modifies the records and commit, and when your transaction comes and updates it, you are going to override the other change without knowing it. Now, actually it gets much more interesting here, because depending on if you're using two-phase locking on MVCC, your perception about what can happen can actually vary. For instance, if you're using two-phase locking and you select the sum of salaries in a department, and then you have a different user in the transaction coming and trying to insert another employee. If you're using two-phase locking because you take locks, the other one is going to block. Until you receive the lock, if you have a time, they will get a timeout if you're taking your time to release the locks. So this phenomenon is going to be prevented. However, if you're using MVCC, in MVCC you don't take locks. So you read the sum, the other transaction can read the sum and actually insert the record. But then when you come back, you have your transaction to fail. So that's why it's called optimistic, because it actually assumes that nothing wrong can happen, but if it happens, it has to detect the failure. However, that was if both are doing reads. If the first transaction does the read, the second one comes, does the insert, and that happens in Postgres, and then you can just update and it will work. Do you think that this breaks serializability or not? You think this is a bug or not? According to the flow of time, it might seem that it's a bug, but it's not. Actually, serializability does not incur any fixed ordering in time. Transactions can still be interleaved. From the database perspective, Bob didn't read anything, so he would have inserted anyway. So that's why here, this is perfect. This is serializable, but it's not strict serializable. It's not linearizable. So that's why that works. But however, you have to understand how these things work, because you might have an impressions of how things will flow, which on an MVCC database might not hold true. If you take the standard, that's how the three phenomena are split by the isolation level that you might have. But in reality, it looks something like that. Oracle only has two, read committed and serializable. The default one, as you can see, allows all phenomena that we've seen, just dirty read is prevented. And for serializable, they call it serializable, but it's not, it's snapshot isolation. Even it allows write skew to happen. SQL Server, the default one uses two-phase locking, so you can see the serializable is going to prevent everything. However, if you're using MVCC, you'd get the snapshot isolation, which works exactly like an Oracle. For Postgres, repeatable read is actually snapshot isolation, but actually they use for serializable a new implementation which is called serializable snapshot isolation, which is quite new. It's from 2009, and when you study database systems, you will see that times flows extremely slow in database terms. It's exactly the opposite, like in JavaScript, where you have a new framework every 6 months. Here you have a new algorithm coming out like every decade. For MySQL, they use still snapshot isolation for repeatable read, which is the default, but for serializable, to prevent everything, they just take locks. And actually, from a consistency perspective, when it comes to concurrency, it's actually the MySQL serializable is much more convenient than for other databases, which is contrary to what people might think. Now, that was ACID, and it actually it allows you, it's very good that you have it, but it's actually not sufficient. You cannot just rely on that, because it was designed in the times of mainframes, like it was that code, you had terminals, and you had one mainframe, you had a two-tier application where you had one connection and you kept it for as long as you need it. Actually, that's not how internet works. Web applications work, you have a workflow or logical transaction which spans over multiple physical transactions. And if you have that, you actually need to use application level concurrency controls. For instance, if you don't do that, assume this very typical workflow where you read a product, and in between you have a batch process which updates the quantity to 0, and when you come back, you assume that the quantity is 5, so you're just going to decrement it, select it, decrement it, and save it. So it's going to -1. So that's bad. The problem we'd have there, it was that service was stateless. As you will see during OLTP application on the front end, they're always stateful. No matter what other people will tell you, it's very difficult to make them stateless. Somewhere you have to retain some state. So here, we're retaining the state for the product. The batch comes and updates the quantity to 0, and then we assume the quantity is 5, as we've seen it before, because we see it on the screen. And when you decrease it, you overwrite it, you still get a lost update, because now from 0, you saved it to 4, which is wrong. So how can you fix it? With optimistic locking. Optimistic locking is an application-level concurrency control which actually addresses application-level concurrency control issues. If you put the version, the update is going to modify. So every time you do a modification, like update or delete, you're going to set the version based on the version that you read. If, for instance, the version was changed, like here initially it was 1, now it's 2, when you come back and you try to overwrite it, and you assume the version is 1, the update count for your update is going to be 0, so Hibernate is going to throw an optimistic lock exception. So actually you're prevented, is exactly like MVCC. You allow conflicts to happen, but you detect them and you prevent them. Actually, using optimistic locking is not as optional as you might think for many use cases. All right, but now that you have optimistic locking and you have this version, for instance, if you have this post with title, views, and likes, and then you have multiple users who read this record, the first one tries to set the title, so it bumps the version up. Now the version is 1. The other one tries to set the likes, but the version was changed, so they get a conflict. And the next one will also get a conflict. So if you're using optimistic locking, that might happen also to you in your application. So what can you do about it? The thing here is a false positive. Actually, the title, the likes, and the other one, which is the views, are not overlapping. There are different concerns. They should be updated independently. So what you can do is just split into multiple one-to-one relations, like you have post with post like with post view. They can even share the IDs. So now you have actually, instead of 1, you actually have 3 records. So when you read, everyone reads the record that they are interested. The first one updates the post, the other one updates the post like, and the third one updates the post views. Now you're not going to get the conflicts. Sometimes you have to split even by write concerns, not just by reading. Now, if you don't want to do that, and if you cannot adjust your schema, you can, in Hibernate, that's not supported in JPA, but in Hibernate you can do something like that. You need to activate dynamic updates to change the update so that only the changed columns, only the columns that have changed will be included in the update. So here we start with the same record, only one post record. Here you can see that no version anymore. It's a versionless optimistic locking mechanism. So now when Alice modifies the title, the update is not going to include all the columns, which is by default, the default in Hibernate is going to only include the columns that have been modified. So the other updates can still go on because they are not conflicting anymore. So that's another way you can address this issue when it comes to conflicting updates. All right? So that's basically pretty much it. Now if you have questions, we can discuss about them. Come on, it's not very difficult. The thing is that most people, as you probably might do, if you go to the project and check the isolation level that you do, I bet that most of the time you're going to use the default. And when you use the default, as you will see, there are many phenomena. It's not that it's necessarily that's going to be a problem for your application. It might be a problem for some class of application, while for others might not be a problem. However, you need to be aware of them. So think about it for one moment. If it's difficult to get it right, even with a relational database which provides so many mechanisms, imagine how difficult it's going to be if you're just using an event log, store everything there, not doing any validation. Because the database actually provides an event log, but it's a validated event log, a linearizable list of set of changes that happen, which you can then scan with the Bayesian and put in Kafka. And actually that works great. Actually, if you just put and accept everything in CQRS, you're not going to do any validation. So now, think about it. Are you really going to do those validations? Chances are, maybe you are going to do them, but chances are you'll have to go back in time and analyze every transaction and figure out if something bad has happened. So actually, it's even more complicated. You get this for free when you're using a relational database. Now, if you don't have any questions, thank you for coming. Hope you like it. Let me take a picture of you.